Hi folks, it's Eric today here to show you a YouTube video on how to blow up a balloon. Well, actually, let me show you what happens if you try to take even breaths, each breath the same amount. Alright, I could have blown that up faster, but I was trying to make measured breaths. And the point is that the first breath, you can see a noticeable increase, a dramatic increase in the size of the balloon. Subsequent breaths, which might have been the same amount of air, did not appear to enlarge the balloon as much. So I want to make this into a qualitative problem by asking you, suppose that we could pump in air at a constant rate. We've got a pump that just pumps at 10 cubic inches per second. Air is being pumped into the balloon at a constant rate of 10 cubic inches per second. How fast is the diameter of the balloon increasing at a moment when, let's say, the diameter is exactly 5 inches, and later when the diameter is exactly 10 inches? Let's take a look. All right, let's remember that what we're trying to do is blow up a balloon. We've got air being pumped in. It's coming in at a constant rate of 10 cubic inches per second. So we've got volume of the balloon and we've got time. So this is volume per unit time. And so we have volume, that is actually the dependent variable, and time is the independent variable. Intermediate between those, which is a quantity that's also referenced in the problem, is diameter. And we're going to view the diameter of the balloon as time dependent. Diameter depends on time, and then volume depends on diameter. So let me just note this is time, this is diameter, volume. When you have the three quantities, time, diameter, and volume, related in that way, then we can write down the chain rule, which tells us dV by dt is dV by dt times dd by dt. So the first thing is to recognize what the basic variables are, usually 3 of them, sometimes more, and then to see what order we should be listing the variables from independent to dependent with something else in between. You're not looking for the rates of change at this point. So if you are thinking about velocity or some other rate of change, you usually don't worry about that until you've listed the basic quantities first, independent of worrying about rates of change. If time appears in the problem, is usually, or very often at least, the independent variable. So experience will tell you something more about what the right variables should be and in what order to list them. Although actually the order that you list them doesn't ultimately matter if you're doing everything else correct. So, point I'll make later. So let's see what else we know in this problem. One thing that we can say for sure is that this is the rate of increase of volume. It's the rate at which volume is increasing per unit time. It's the rate of change of volume per unit time. Now it's actually the average rate of change as well as the instantaneous rate of change, just because that rate of change is a constant. In other problems, this will be a variable quantity, but in this case, it just happens to be a constant. So this is actually what dV by dt is. It's 10 That's what this is telling you. Okay. Now, there's one other derivative in here that we know, which is dV by dt. If you can write the volume in terms of diameter, there's a formula for that. Usually we write the volume in terms of radius. So you look up that formula. Volume is 4/3 pi r cubed to write the volume of a sphere in terms of the radius. And now the diameter is twice the radius. And you can substitute that in here. 4/3 pi d over 2 cubed. Simplify. Pi over 6 d cubed. And if you know how volume depends on diameter, then you can take that derivative and let's just work it out. So dV by dd. So it's the power rule. And you bring down the 3, get a little simplification. This ends up being pi over 2 d squared. So always remember when you're taking derivatives, the question is derivative with respect to what? The volume has two relevant derivatives in this problem. So there's the derivative of volume with respect to diameter. That's a rate of change. It tells you for a small increase in diameter, what's the comparable or proportionate increase in volume. This is telling you for a comparable, for a small increase in time, like a second, how much is the increase in volume? 10 cubic inches. And so that's a different rate of change. They're not the same thing. But they are related. These different rates of change are related by the chain rule. So let's go ahead and substitute this answer into here. And then it's times. So there's our formula that tells us the rate of change of diameter with respect to time. I can solve for that and get dd by dt. And I get 20 over pi d squared if I did the arithmetic right to solve. Now, let's not worry about time at the moment. Let's just think about how this rate of change depends on the diameter. I can actually plot this. It's a graph that is a power function that goes down like this. It's got a vertical asymptote here, horizontal asymptote here. So I'll label the axes. And this graph is telling me how the rate of change of diameter decreases as the diameter itself increases. So for a small diameter, you actually see the balloon increasing rapidly. When the diameter gets larger, you don't see the increase as much because it's a smaller rate of change. So the shape of this graph is answering the qualitative observation we made just by blowing up a balloon. Now we have a quantitative question here, is to look at what happens when the diameter is 5 inches or 10 inches, and then we just pick off these 2 points of the graph and we just substitute in to see what values we get there for the rates of change. So in the first case, we're taking the rate of change of diameter per unit time, and we're looking at what happens at d equals 5. So this notation just says you take this formula, you evaluate that at d equals 5. This is a general formula that works for the entire expansion of the balloon. This is asking what happens at one point in time. And since we're not given time explicitly, we're just given the diameter, that's what you substitute in. It doesn't matter what time is here to answer the problem. You don't need time. You can just substitute in d equals 5. So I just substituted into this formula. That is about 0.25 inches per second. Notice the units here. Rate of change of diameter with respect to time take the units of diameter, which is inches here, divide by the units of time, and that's seconds. So you get an answer in inches per second. So that says at this point during the expansion of the balloon, when the diameter is reached to 5 inches, when the balloon is 5 inches in diameter, it's increasing at about 1/4 of an inch per second. That's the instantaneous rate of change. Now, at a later time, you should expect a smaller number. And that's exactly what we get. So we take this general formula. This time we evaluate at d equals 10. So we just plug in 10 into this formula. Over 5 pi. My calculator makes this out to be about 0.064 inches per second. So when the diameter is 5 inches, it's increasing at a rate of about 0.25 inches per second. Later, when the diameter has reached 10 inches, it's increasing at a rate of about 0.064 inches per second.